Welcome back. In this video we're going to look at Rolle's theorem, and we're going to also look at a slightly more generalized version of it, which is called the mean value theorem. Now this is a really useful thing, and it tells us something about what the derivative of a function must behave like in between 2 points where we know the values. So we'll dive straight in and look at Rolle's theorem first. Okay, so the setup for Rolle's theorem. We have a continuous function on a closed interval a, b. So let's draw ourselves a continuous function on a, b. Here's a, here's b, and here is our continuous function f of x. Okay, so it's continuous between a and b. Outside of that, who cares? And it's differentiable on the open interval a, b also, which means it doesn't have to be differentiable at the endpoints, but it definitely has to be continuous there. Okay, the theorem says that if f of a equals f of b, now that's where we see if I drew my picture badly or not. So if I go up to a here, and I get the same value as I get at b, so that's f of a, which is also equal to f of b, then Rolle's theorem tells us that there is a point somewhere in between, which in this case will be about here, where f prime of c is equal to 0, i.e. the curve is flat. Okay, so that's the theorem. We need to go and figure out how we can go about proving it. Okay, so let's start by getting a little bit of intuition about what we're dealing with. We know what our setup looks like. We know it's continuous on a closed interval. Now hopefully hearing continuous on a closed interval jogged your memory slightly, and you may have recalled something else we did, something else that we get for free if a function is continuous on a closed interval. And that is the extreme value theorem, which is that the function has a maximum and a minimum value. Okay, so there aren't that many things that can be happening here. If we think about where the maximum could be for our function, well, maybe it's, if our function looks something like that, then the maximum is somewhere in between a and b. Okay, but our function could also potentially look something like this, in which case the minimum is still going to be between a and b at some point c. And the only way the maximum and the minimum could be at the endpoints is if our function in fact was flat all the way along. Okay, so if the maximum and the minimum are both at the endpoints, then our function would have to look like this, because as soon as we deviate from that straight line, then the maximum is going to have to, or the minimum is going to have shifted to some point in between. Okay, so by the extreme value theorem, f of x has a maximum and minimum value on AB. If both are at endpoints, then f prime of c equals 0 everywhere. Okay, as function is constant. So we can do away with that weird case first, where we just have a constant function. And otherwise, we're just going to assume that we have a maximum somewhere between a and b. Now, we may have a minimum instead, in which case we could turn our function upside down. But we'll just, without really losing any generality for our argument, we'll assume maximum is at c for some c in between a and b. Okay, so what we're going to do is, here's our setup now. We're assuming our curve is this way up, just for the sake of argument. Remember, the function values are the same at the endpoints. Here's a, here's b, and we're assuming our maximum value is here at c. Now what we're going to do is we're going to argue that if we construct a sequence on this side of c and another sequence on this side of c, and look at the difference quotients i.e. the derivatives, we're going to see we have a positive derivative, or this limit is going to be a positive thing on the left-hand side, and it's going to be negative on the right, because this has got a positive slope here, and on the right it's going to have a negative slope. So that argument should lead us to our slope being equal to 0, or our derivative being equal to 0 at c. Okay, so let's just write down how we can do this. Because c is in our interval, we can construct sequences okay, so we'll call one of them xn and one of them yn, both of which converging to c, satisfying, we'll put xn on the left of c, so we'll call the green one our sequence xn down here, and we'll call this red one our sequence yn. So they're going to satisfy xn is less than c is less than yn for all n in the natural numbers. Okay, so now we're going to compare the two, look at the two differential quotients of this situation here. So we know f prime of c equals the limit as n tends to infinity. Okay, so we're doing a sequence limit here. We can write it this way. We don't normally use this notation for our sequence limits, but this is fine. Of f of yn minus f of c, all divided by yn minus c. Okay, now let's look at the sign of this thing. Remember, f of c is our maximum, which means this term overall is therefore got to be negative. Okay, because f of c is a maximum. And likewise, on the bottom here, this term is positive, because yn is to the right of c, so yn minus c is positive. And so this thing here has got to overall be less than or equal to 0. But also, if we do the same thing again, but use our xn sequence instead, f prime of c equals limit as n tends to infinity of f of xn now, because this limit has to be true no matter what sequence we take that converges to c, just from our sequence definition of limits, has to equal this limit as well. And this one, f of xn minus f of c, is still going to be negative, but now the bottom of our fraction is going to be negative as well. So this term is negative and positive. Sorry, negative and negative. Let's get that correct. The top is still negative like it was before. So overall, this has got to be greater than or equal to 0. The only way for those things to both be simultaneously true, which they must be because we know f is differentiable at c, is for f prime of c to equal 0. Okay, so Rolle's theorem tells us that at a maximum, a differentiable function has 0 derivative. Okay, so now that we've got Rolle's theorem under our belts, we can look at a slightly more general version of the same thing, which is the mean value theorem. So you notice we've got the same setup. We've got a function that is continuous on a closed interval ab and differentiable on the same open interval. This time we've got the existence of a point rather than f prime of c being 0, which is what we had when f of a and f of b were equal. If they're not, then the point in question satisfies f prime of c equals f of b minus f of a over b minus a. Okay, so what we should do first is sketch a picture of what this looks like, just to get our heads around it. So let's draw ourselves our curve. So here is our function. Here is f of x. And here is a. And here is b. And we have corresponding values f of a now and f of b. We're no longer requiring them to be equal. Now what the mean value theorem says if you look at this quotient f of b minus f of a over b minus a, that is this distance along here divided by this distance along here. So it's like a rise over run type expression. So if we were to draw in a straight line going through those 2 points, then what this says is that there must be a point on my function where the derivative is equal to the slope of that straight line. Okay, so you can see that it's kind of like a warped version of our Rolle's theorem picture. We draw a straight line connecting the 2 endpoints up, and we have to find a point on our function where the derivative is the same as the derivative of that straight curve, or the slopes are the same thing. Okay, so let's write down an equation for this line. So the line is y equals slope. Okay, so it's going to be a little bit messy, but it all is just stuff we've done before. Slope times x minus a plus f of a. Okay, and you can sanity check this. If you put in x equal to a, then the first term will disappear, and we'll just get f of a. That's right. If you put in x equals b, then x minus a becomes b minus a. The b minus a's will cancel, and so will the f of a's, and we'll get f of b. So that is the right equation of a straight line. So what we want to do is we don't want to try and do the same kind of argument all over again, because it looks very similar to Rolle's theorem, just like it's been shifted around a wee bit. So what we're going to do is we're going to define a new function, which we'll call d of x, and it's just going to be this distance here. In particular, we're going to say d of x equals f of x minus y equals, and then we can plug in all the bits and pieces, f of x minus f of b. Okay, it's horrendously messy, but again, it's all just straight line equations, so it's not quite as bad as it looks, minus f of a. Okay, the point of doing this is, this function, d of x is equal to 0 at this point, and also at this point here. Okay, so it has the same values at both ends, and so Rolle's theorem is going to apply to it. And so the slope of d of x is going to be 0, it will turn out. And you can see why, because the difference of the two slopes should be 0. So if we apply Rolle's theorem to d of x, we should find that this point that has 0 slope will also give us the right point for our original function f. So with a bit more extra space available to us, we'll look at this function and we'll apply Rolle's theorem to it. So note, d of a equals 0, which also equals d of b. Again, I encourage you to actually plug it into the formula and double check that works out, but it does. So Rolle's theorem gives us a point C in our open interval such that d prime of C equals 0. Okay, so d prime of x, if we were to take our function and differentiate it, that's going to be f prime of x minus f of b minus f of a, just differentiating the normal way, divided by b minus a. The next term is a constant, so is the next term after that. That's d prime of x. So if d prime of c equals 0, then f prime of c has to equal f of b minus f of a over b minus a. So that's quite nice. We managed to use Rolle's theorem to give us a leg up and actually prove this more general theorem about mean values. So it kind of says that there is somewhere in between those 2 points where the slope of our curve is the mean value of the slope, and in the sense that we take an average slope over the interval by looking at the 2 endpoints, and it guarantees for us that there is a point somewhere in between them where we get that same slope. And before we leave this behind, there's one more mean value theorem that we'd like to have a look at, and it's the so-called generalized mean value theorem. So now we have two functions f and g, both being continuous on the closed interval ab and differentiable on the corresponding open interval. This time there exists a point C in the open interval such that this particular expression here, which is like a combination of differences and derivatives, is true. And if our g prime of C is not equal to 0, then we can also write that as the ratio of the two derivatives is equal to the ratio of their two differences. Okay, now it turns out this one is sometimes quite useful in practice. And the proof of it is not too hard because we've kind of done it already. So we'll leave it as an exercise, but the way you go about it is you apply the mean value theorem to the following function. H of x equals f of b minus f of a times g of x minus g of b minus g of a times f of x. And then the result that we're after kind of falls straight out. Okay, so that's enough about mean value theorems for today. We'll see you next time.